I've got a challenge for you, and I need to spend a little bit of time explaining it. I've drawn part of the graph of a function here. I've just graphed 2 points, okay? So we've got a f of a down here. I'm actually going to just label that that's down at a height that I'm calling here. That's where the y value of that point is. And then b f of b is up there. I'm going to just label that the height of the function at b is up there. Okay, so I've sort of labeled down here, up there. And I want to just observe that the x-axis, where we would have a y value of 0, is in between. So down here, our y values are negative. Up there, our y values are positive. And in between, on the x-axis, our y values would be 0. Okay. Now, the challenge is for you to draw a function such that the domain is the closed interval from a to b. So, has to include this point and this point, okay, and has to have a point for every x value in between a and b, okay. And you need to start here and end there, so that we'll have f of a is less than 0, which is less than f of b. Okay, and what I would like you to try to do, and go ahead and pause the video to do this, try to draw me a function that satisfies those two conditions. It can be done. Pause the video, see if you can figure that out. Welcome back. I'm going to just draw one possible solution. I'm going to just jump over the x-axis. Now here I haven't quite met the conditions yet, because the domain was supposed to be everything between a and b. By jumping from a hole to a hole, I don't have whatever this x value is here, that's not in my domain. So I either need to fill in one of the holes, which I think I'll do, or if I wanted to, I could put a point anywhere else. Now, for every x value between a and b, including those endpoints, I've got a point, and I started down here, and I ended up there. I introduced a jump discontinuity so that I could jump over the x-axis. So, if you were struggling to find an example of this, you were assuming probably that your function had to be continuous. But I didn't say that. Now, when I teach this class in person, I have a lot of fun with this, because then I say, now let's try to make this more challenging. Let's require that f be a continuous function. And then I stand in front of the class, and I'm a mean, horrible person for doing this, I know, and I say, can anybody draw me a function that meets these conditions? And I hold out the marker as an enticement. Wouldn't you be so excited if you could meet this challenge? And then I say, let me rephrase the question. Can anyone draw a function that meets these conditions? It's a yes or no question, to which the answer is no. That challenge, it is not possible to meet. Okay? In order to go from here to there, I either have to cross through the in-between zone or jump over it. If I've got a continuous function, I'm not allowed to jump over it, so we would have to pass through it. And so that's basically what the intermediate value theorem says. I've sort of given you the common sense version of things, that you can't get from here to there without passing through what's in between if you're a continuous function. So here's how it's formally stated. Intermediate value theorem. Okay, so it says if f of x is continuous on the closed interval from a to b. Okay, so it does have to be a finite closed interval, like so, including those endpoints. Okay, and if n is any number between f of a and f of b. So these y values are establishing a here and a there. N is establishing our in between. A very common choice for n is 0, just because it's so easy to tell whether something is bigger than 0 or smaller than 0. You basically have smaller than 0 is negative, bigger than 0 is positive. Okay. But if we have this, okay, then there is an x value c somewhere in the interval from a to b, such that f of c is equal to n. Okay. This basically just says that that challenge I gave you a moment ago is impossible. Okay. So a couple of things to point out. Okay. First of all, the function does have to be continuous on a finite closed region like this. Then you've got to have this, that n is in between things. Now ordinarily we will express that as an inequality. That's going to either mean that f of a is less than n is less than f of b, or f of b is less than n is less than f of a. Okay. Doesn't matter which one's biggest and which one's smallest. What matters is that you have a here, a there, and an in-between, and n is the in-between thing. So for any particular examples, rather than writing this out in words, I would use the appropriate inequality. But for the general statement of the theorem, we generally state it in words simply because we don't know whether f of a or f of b is the bigger of the two y values that we have at the endpoints. Okay. All right. And then this just tells us that there is an x value c in this interval. I could actually, if I wanted to, have parentheses here, because as long as these are strict inequalities, then I know that the location of c isn't at one of the endpoints, because then I would have to have inclusive inequalities here. Okay. So you can state it with either a closed or an open interval here, but this one has to be closed. Okay. So if you want, you can just play it safe and always use the closed interval, but common sense tells us the location where this occurs is not going to be at one of the endpoints, such that f of c is equal to n. Okay. All right. So the picture that goes with this, I always kind of like to have a picture, is that if I've got an a and a b, I'll draw this one so that f of a is the bigger one. So that's up here, and f of b is down there, and n is anywhere in between. Now I mentioned very often n is going to actually be 0, so that it's in between a positive and a negative number, but it doesn't have to be. Okay. And all this says is, hey, if I want to play connect the dots, I'm going to have to cross that line somewhere. There's no way I can avoid it. I'm going to have to cross it. Okay. So where I've crossed it, I'm just giving a name c to that. When I plug in c, I get n. I should just point out, there's nothing that says I can't cross it multiple times. So the theorem does not say there's a unique x value c. It says there's at least one where this happens. All right. Now in the next video, we'll take a look at actually using the extreme value theorem to prove that a polynomial that we're not able to factor completely to find all of the roots actually has a root or a 0 in a particular interval. That's one of the nice uses for this. When you can't solve an equation exactly, you can sort of approximate it by using the intermediate value theorem. Okay. Just want to point out, we know the intermediate value theorem is true. This is a gift to us from the mathematicians that have gone before. They have proved it. It's not our job to prove this. When we're proving an if-then, we suppose the if and show the then. When we're using an if-then, which is what we'll be doing here, we have to show that the if part is true. So we are going to have to state that our function is continuous on a finite closed interval. we are going to have to state that there is an inequality that puts n in between the function value at the endpoints of that interval. And then we just state our conclusion, that there is an x value at which we will actually hit that in between y value. Okay,